So good evening. So today we will be presenting for our group project for computer organization and architecture. So our group project is about CPU and hardware benchmark. So in our group we have me, Goh Siang, and then my members here. Please introduce yourself.
Me, Liu Shannon.
Hi guys, my name is Sun Hong.
Okay, hello guys, my name is Khairul Hakim.
Okay. So about our project, we'll be doing benchmark. So what is benchmark? Benchmark is a test that is conducted to measure and compare the performance of the hardware, software, or the entire computer. So by doing benchmarking, we can have a clear picture of the performance of a computer system in handling situations that were given. Through benchmarking, we can also tell that whether a computer is faster at finishing a given task than compared to another computer. So next slide. So for problem background, so in this digital era, we have a lot of computers that come in all sorts of shape and different components. This causes each computer to have different performance depending on the hardware that is running and also the software that's powering the computer. So to grasp the capability of each computer that's running, basically to grasp the capability of each computer system, we can conduct benchmarking on this computer system to know which computer system is more suitable for the tasks that are being provided. Next slide. So for our aim, we will be conducting benchmarking on computer system to gain insight on computer performance, hardware difference, and intricacy of software optimization. The objective is to carry out CPU benchmarking on computer system, to compare performance of CPU of different computer system and identify the best performing computer. And then the third one is to analyze the result obtained on the impact of different workload towards CPU performance. And then our scope is, in this project, we will be doing benchmarking using different benchmarking software such as CPU-Z, Geekbench, Minitools, and Windows Task Manager, and also a polynomial equation algorithm benchmark, which is by using assembly code that we type ourselves to test the performance of the computer system. And also in this project, we will compare and analyze the performance of each computer system by using the obtained benchmark result to identify the best performing computer system. So I will pass the presentation to my friend Sun Hong here.
Okay, thank you, Gary. And next, I'm here to share the benchmark results for 4 computer systems, Gary's, Liu, Neo's, and Kyrill's. We will go through the numbers from each test we ran. First, let's look at the information from CPU-Z. This gives us details about their parts. Gary's computer has an AMD Ryzen 7 7435HS CPU with a clock frequency of 2637.09 MHz when idle and 3991.92 MHz when stressed. For each cache, it has a level 1 instruction at 8 times 32 kilobytes, level 1 data at 8 times 32 kilobytes, level 2 at 8 times 512 kilobytes, and level 3 at 16 megabytes. It has 16 gigabytes of DDR5-5600 memory with DRAM frequencies of 2800 megahertz. Its motherboard model is FA500-07NVR with an AMD Ryzen SoC chipset and PCI-Express 4.0 bus. For Liu's computer has an Intel Core i5 12450H CPU with a clock frequencies of 3192.19 MHz. Its cache includes level 1 data at 4 times 88 kilobytes plus 4 times 32 kilobytes. Level 1 instruction at 4 times 32 kilobytes plus 4 times 64 kilobytes. Level 2 at 4 times 1.35 megabytes plus 2 megabytes. And level 3 at 12 megabytes. It has 16 GB of DDR4-3200 memory with DRAM frequencies of 1596.1 MHz. Its motherboard model is Gemini_ADH version 2.09 with an Intel Alder Lake chipset and PCI-Express 4.0 bus. Now let's look at Neo's computer. Neo's computer also has an Intel Core i5 12450H CPU with a clock frequencies of 2394.14 MHz. Its cache details are the same as Liu. It also has 16 gigabytes of DDR4 memory with DRAM frequencies of 1596.1 MHz. Its motherboard model is 8C3F with an Intel Alder Lake chipset and PCI-Express 4.0 bus. Lastly is the Kyrill's computer. For Kyrill's computer, it has an Apple M4 CPU with an idle frequency of 1352 MHz and a base frequencies of 4.41 GHz. For its cache, it has level 1 data at 4 times 138 kilobytes plus 6 times 64 kilobytes. Level 1 instructions at 4 times 192 kilobytes plus 6 times 128 kilobytes. Level 2 at 1 times 16 megabytes shared among 4 P cores plus 1 times 4 megabytes shared among 6 E cores, and level 3 system level cache at approximately 8 megabytes. It has 16 gigabytes of LPDDR5X memory with frequencies of 7500 MHz. Its model is MAC 16, 1. Next slide, please. Now for the task manager results showing CPU and memory used under the different loads. For Gary's computer under low load, CPU was 7%, memory 63%. For medium load, CPU 15%, memory 72%. For high load, CPU 31%, memory 89%. For Liu's computer under low load, CPU was 14%, memory 35%. For medium load, CPU 13%, memory 45%. And for the high load, CPU was 34%, memory 77%. For Neo's computer under low load, CPU was 4%, memory 45%. For medium load, CPU 4%, memory 56%. For high load, CPU 22% and memory 70%. For Kariu's computer under low load, CPU was 2%, memory 38%. For medium load, CPU 5%, memory 61%. For high load, CPU 17%, memory 76%. Next slide, please. Thank you. Moving on to the Geekbench benchmark results, which give us single core and multi-core CPU performance score. Gary's computer score 1,804 for single core and 7,323 for multi-core. Liu's computer score 1,534 for single core and 7,035 for multi-core. Neo's computer score 1,520 for single core and 6,864 for multi-core. And lastly is the Kariu's computer, which score 3,673 for single core and 14,275 for multi-core. Next slide, please. Next, we have the Mini2 benchmark result showing external disk performance for sequential and random data access measured in megabytes per second, MB/s. For Gary's computer, sequential reads range from 457.836 megabytes per second, which is 4 KB, to 1600.32 megabytes per second, which is 32 kilobyte, and writes from 184.868 megabytes per second, which is 4 KB, to 1159.2 megabytes per second, which is 32 kilobyte. For the random data access, random reads range from 336.882 megabytes per second to 1035.31 megabytes per second, and writes from 210.911 megabytes per second to 787.437 megabytes per second. For Liu's computer, sequential reads range from 1031.39 megabytes per second to 2099.12 megabytes per second, and writes from 970.739 megabytes per second to 2746.45 megabytes per second. Random reads range from 675.764 megabytes per second to 2191.5 megabytes per second, and writes from 971.759 megabytes per second to 3332.22 megabytes per second. For Neo's computer, sequential reads range from 486.133 megabytes per second to 1798.79 megabytes and writes from per second, and writes from 215.719 megabytes per second to 1311 megabytes per second. Random reads range from 443.679 megabytes per second to 1348.77 megabytes per second, and writes from 256.634 megabytes per second to 1313.2 megabytes per second. Lastly, for Kariu's computer, we tested via the FIO because it used the Mac OS, and for the sequential reads, we obtained the range from 1588 megabytes per second to 2712 megabytes per second, and writes from 1589 megabytes per second to 2710 megabytes per second. Random reads range from 212 megabytes per second to 503 megabytes per second, and writes from 212 megabytes per second to 512 megabytes per second. Next slide, please. Thank you. Finally, the polynomial equation algorithm benchmark results shows the execution time in milliseconds for different number of loops, and we are using the Visual Studio 2019 for this test. For 50 loops, Gary's computer took 5,396 milliseconds. For 100 loops, Gary's took 10,793 milliseconds. For 200 loops, Gary took 31,637 milliseconds. For 500 loops, Gary took 54,024 milliseconds. For 700 loops, Gary took 75,590 milliseconds. And lastly, for 1,000 loops, Gary took 108,069 milliseconds. Next slide, please. For Liu's computer, it took 5,491 milliseconds for 50 loops, 11,087 milliseconds for 100 loops, 22,132 milliseconds for 200 loops, 55,437 milliseconds for 500 loops, 77,483 milliseconds for 700 loops, and 110,330 milliseconds for 1,000 loops. Next slide. Neo's computer took 5,684 milliseconds for 50 loops, 10,895 milliseconds for 100 loops, 32,105 milliseconds for 200 loops, 51,905 51,978 milliseconds for 500 loops, 74,159 milliseconds for 700 loops, and 104,286 milliseconds for 1,000 loops. Next slide. Lastly is Kyrie's computer. It took 2,968 milliseconds for 50 loops and 5,993 milliseconds for 100 loops, 11,958 milliseconds for 200 loops, 29,961 milliseconds for 500 loops, 41,883 milliseconds for 700 loops, and 59,638 milliseconds for 1,000 loops. That's cover all the results from our test. And now I will pass my speech to my another teammate, Hakim. Thank you.
Okay, so I'm going to present for the comparison and discussion. All right, so we proceed with the CPU clock frequency and memory size and memory frequency from CPU-Z result. So for the CPU and clock frequency, we can see that Gary's computer leading the chart by quite a lot, which scored 3,991. Meanwhile, the second one is Gary's computer, which is scoring 3,520, followed by Liu's with 3,192, and Neo's the last one with 2,394. Next, for the memory size, although all computers have the same memory size of 16 gigabyte, the memory frequency here varies. Scoring the highest is Kyrie's computer with 7,500 megahertz per second, and the second one is Gary's computer with 2,800 megahertz. The third one and the fourth one, which is Liu's and Neo's computer, having the same memory frequency with 1,596 megahertz. So moving on to Geekbench 6 benchmark results comparison, we can see Kyrie's computer leading by quite a lot, maybe about twice. Here for the single core, he scores about 3,673 for single core and 14,275 for multi-core performance. Following the second is Gary's computer with the single core performance of 1,804 and for single core, and for multi-core 7,323. And the third one is Liu's computer with single core performance of 1,534 and for multi-core performance 7,025. And last but not least, Neo's computer with single core performance of 1,520 and multi-core performance of 6,864. So for the Mini2 benchmark results, here we can see the difference in speed for sequential and random type of task. So for this performance for sequential, we can see Kyrie's and Liu's computer actually dominates this category, ranging from 4 kilobytes read and write up until the 32 kilobyte read and write. For this performance on random, we can see that Liu's computer actually taking the lead here for 4 kilobyte read and write. Meanwhile, for the 8 kilobyte read, it is actually led by Gary's computer. And then for the 8 kilobyte write, Liu's take the lead back with 1,854. For the 16 kilobyte read and write, again, Liu's computer lead the chart. And for the 32 kilobyte read and write, also Liu's computer lead the chart by 1,863 for the read and 1,397 for the write. Okay, so for the execution time for polynomial equation algorithm using Visual Studio 2019, we can see for this chart, we can see that Kyrie's computer taking the shortest executed time, which roughly half from other computers, scoring for 50 loops 2,968, and for the 1,000 loops 59,638. Meanwhile, the one that took the longest execution time for 50 loops is Neo's computer for 50 loops with 5,684 millisecond, and for the 1,000 loops, the ones taking the longest execution time is Liu's computer with 110,330 milliseconds. Okay, so for the discussion from this analysis, we compare the performance of 4 computer systems, which is Liu with Intel i5 12450H, Neo's Intel i5 12450H having the same CPU, Gary's AMD Ryzen 7 7435HS, and Kyrie's Apple M4 chip processor. All systems have 16 GB of RAM, but it varies in clock and memory frequencies. So the key findings here is for the CPU and memory, Kyrie's computer consistently lead in CPU clock frequency, memory frequency, and both single and multi-core Geekbench CPU scores, followed by Gary's, Liu's, and Neo's. For this performance, Kyrie excels in sequential disk speed, meanwhile Liu shows the best overall disk performance due to superior random mode speeds. And then for the algorithm execution, Kyrie's computer executed polynomial functions algorithm fastest, followed by Gary's, Liu's, and Neo's. So overall, Kari's computer demonstrated the best overall performance, leading in most CPU memory and algorithm execution benchmarks. Gary's followed as second best. Liu's placed third despite strong random performance, and Neo's computer consistently ranked last. Okay, so I'm going to pass to my fellow friends here. Thank you.
In conclusion, we have found that Kari's computer is the best performing computer among the 4 computer systems that have been benchmarked. This is followed by Gary's computer that ranks second, Liu's computer at third rank, and Neo's computer at the last rank. From this project, we were able to learn how to benchmark a computer system using available benchmark software and to gain insights on the computer performance from the benchmark results. By carrying out benchmarks, we may also make an assumption on the performance of another computer by comparing the hardware and software running on the computer by comparing it with another similar computer, so that we may able to know a computer system's performance in running certain software before buying a computer system. So next is the reflection.
Okay, so for my reflection, say that benchmark has allowed me to know the performance of my computer system so that I may know the limit that I can push on my computer system. Also, the benchmark result also gives me some insight on which part of my computer that I may upgrade in the future to increase the performance of my computer. Lastly, the benchmark also showed me how different hardware can affect the performance of a computer system, and through benchmark, I may detect if whether there's hardware problem that may affect my computer's performance also. Then I will pass to Liu for his reflection.
So for my reflection, throughout this project, CPU benchmarking allows us to evaluate and compare the performance of different processors. The benchmark result shows that different CPUs have different performance in various aspects, such as single core and multiple performance, clock frequency, and speed of executing instructions. The performance of the same CPU also will be different depending on the software environment, thermal condition, and power consumption. Lastly, benchmarking results also help me more clear understand the peak performance of my laptop and the parts that need to be upgraded to improve performance in the future.
Okay, for my reflection, I really learned the power of benchmarking. Now I can actually test the computer CPUs and hardware performance by myself, which is huge for me as a computer science student, especially when thinking about buying a new laptop or understanding my current one better. It helps me to see its strengths and limitation, and also where I might upgrade in the future.
Okay, for me, this project provided an opportunity for me to personally evaluate my device's performance, because previously I just rely on online resources from tech websites and YouTube. So I gained a practical understanding of how my CPU, memory, and disk speed actually directly impact the overall computer performance. The benchmark also allows me to determine the actual capabilities of my hardware, and these new insights enable me to realistically estimate how far I can push my computer for various tasks, be it day-to-day tasks or demanding tasks that I would encounter further and in my university course, allowing me to align the CPU power requirement with its demanding applications. And also, it does transform my understanding of my device from abstract concepts to concrete and actionable knowledge that would be highly valuable in the future, especially when it's time to upgrade my computer for my use case when it demands it. So I think as we finish our reflection, that's all from us. Thank you so much.